Hey students, welcome to lecture number 8 of Linear Algebra 2. So today we want to continue on talking about eigenvalues and eigenvectors. So last time we introduced these, and if we have a linear map F going from one vector space to itself, then a vector V was called an eigenvector if I apply this map F to this vector V, it just gets multiplied by a number lambda, which is called the eigenvalue of this eigenvector, or of this linear map. And we just allowed vectors to be eigenvectors, which are non-zero. And today we want to continue talking about these and also prepare some applications for later. And for this, first recall that we had this example of Fibonacci numbers, which was motivated by counting the population of these bunnies. So we had this linear map F from R2 to R2, which was given by multiplying with this 2 by 2 matrix here. And so we started with a vector 0, 1, which then got mapped to 1, 1, 1, 2, 2, 3, after applying F again and again. And in the end, after n steps, the entries of these vectors was given by these so-called Fibonacci numbers. In our bunny example, these numbers represented the number of bunnies after n months. And we wanted to calculate an explicit formula for this Fn. And so what we wanted to do is we wanted to calculate this matrix A multiplied n times with itself. So we needed to calculate this power a to the n. And this was done by considering these two vectors, v1, which was 2, 1 plus square root of 5, and v2, 2, 1 minus square root of 5. And then we saw that if we define the matrix S by the following, so we put these vectors into this matrix, then if we multiply A with S from the right and with its inverse from the left, then this was given by a simple matrix which just had entries on the diagonal. So here it was 1 minus square root of 5 over 2, 0, 0, and 1 minus square root of 5. Or here it was a plus and here was a minus. So in other words, it had a form like this. So I had some entry here, d1, and here d2, and the rest was 0. And with this, it was quite easy to calculate a to the power of n, because here I can multiply from the right with the inverse, so I can put s inverse here and s here. And then if we take this to the nth power, we thought that this basically just meant we needed to take these diagonal entries to the nth power, and here we still had s and s inverse. And with this, you got an explicit formula for this a to the n, and then we could multiply it by this vector 0, 1 and got this formula for Fn. So and what does this has to do with eigenvectors? Well, in this example here, why this works, the reason is that these vectors v1 and v2, so if you multiply a with v1, you will see that this is actually 1 plus square root of 5 divided by 2 times v1. So in other words, this vector v1 is an eigenvector of this matrix with eigenvalue given by this number here. So this is just d1 times v1. And similarly, if you do this, you can check that a times v2 is this other number d2 times v2. So this was another eigenvector of this matrix A, or of this linear map F. And in this example, we thought that if we find eigenvectors like this to bring this matrix into this diagonal form, this is quite nice, because then we could calculate what happens if I apply this linear map again and again, because taking the nth power of a diagonal matrix is quite simple. So then you might ask, in general, if I have an arbitrary linear map, which maybe describes some population or something like this, and I want to see what happens after applying this map again and again, can I maybe always do this trick here? Can I maybe always find some vectors like this and then define this matrix S such that I get this diagonal form. So the question is, does this work for any linear map or any matrix? And the answer to this question is no. So this doesn't always work. And this is why this property, if this works, also gets a special name. And this is what we want to talk about today. So when is it possible to find a diagonal matrix, or this matrix S, such that a linear map written in a certain basis can be written as a diagonal matrix? And that's why we introduce the following. So from now on, we will always work with finitely generated vector spaces. So the matrices attached to our linear maps are always defined. And also, so this notion of eigenvector and eigenvalue was defined for an arbitrary vector space, but from now on we always assume that our vector spaces are finite dimensional. Okay, so with this we want to define the following thing. So let V be an n-dimensional vector space, and now we have a linear map F from V to V, and then this linear map is called a diagonalizable if there exists a basis of this vector space V such that the matrix of this linear map with respect to this basis is given by a diagonal matrix. So in other words, there are some numbers d1 up to dn, some real numbers which are here on the diagonal, and all entries besides the diagonal are 0 here. And if you can find such a basis, then this F is called diagonalizable. So we can diagonalize this linear map, meaning we can bring it into this diagonal form. And also this notion exists for a matrix. So if we have an n by n matrix, then this n by n matrix is called diagonalizable if we can find a matrix S, an invertible matrix S, such that S inverse times A times S is also given by a diagonal matrix. Okay, and today we want to see when is a linear map diagonalizable, and also make some further statements on this. But first, so now we defined it for a linear map and also for a matrix. And this first statement is that this is basically the same. So if I have a linear map F and B is some basis, then the following statements are equivalent. So if this linear map F is diagonalizable, then also this matrix attached to an arbitrary basis of this linear map is also diagonalizable. And here I will just make a comment on the first direction, and the other direction you can find in the lecture notes. So let's see, if the linear map F is diagonalizable, why is this a matrix F for some random basis of V? Why is this matrix also diagonalizable? So if F is diagonalizable, so this means we can find a basis, let's call it B prime, such that the matrix of this linear map F with respect to this basis has a diagonal form. And now we want to show why for this fixed basis B, this matrix here, this F, the matrix of F with respect to this basis, why we can find a matrix S such that if we multiply the inverse from the left and the matrix S from the right, why this also has this form. Well, but what we can do here is we can consider the change of basis matrix. So if I have this matrix here of F with respect to this basis B, then if I multiply from the right with a change of basis matrix, where I go from the basis B prime to the basis B, and on the other side if I multiply with a change of basis matrix going from the basis B to B prime, then this is just, we learned that this is the matrix of F with respect to the basis B prime, and therefore this is just given by this diagonal matrix here. Because B prime is a basis such that this F has a diagonal form, which existed because this F we assume is a diagonalizable. But now I can just say, okay, this I take as my matrix S. And then we also learned that the change of basis matrix from B prime to B, the inverse of this matrix is a change the basis in the other direction. So if I call this matrix S, then this matrix is exactly S inverse. And therefore this matrix here is diagonalizable because we can find the matrix S. If I multiply it from the right and the inverse from the left, I can bring it on a diagonal form. And the other direction is also straightforward, but a little bit more technical. But for now, it's just important that there's not really a difference between talking about the diagonalizability of a linear map or of a matrix of this linear map for some random basis B. And often in the application, we have a linear map F, and the matrix of this linear map F we consider usually with respect to the standard basis given by these vectors 1, 0, 0, 0, 0, 1, and so on. And then we want to diagonalize this matrix, which then, by this lemma, will tell us that this linear map F is diagonalizable. Okay. So, now the answer of the question, when is a linear map actually diagonalizable? So if I have a linear map F, and now assume I have a basis of this vector space V, B1 to Bn, so the dimension of this vector space is n, such that all of these vectors are eigenvectors of this linear map. So meaning if I apply F to the basis vector Bi, then this is some number di times Bi. So this Bi is an eigenvector of this linear map with eigenvalue di. And then the statement is, if such a basis exists, then F is diagonalizable, and the matrix of F with respect to this basis is exactly the diagonal matrix where the eigenvalues are on the diagonal. And also conversely, if F is diagonalizable, then I have a basis of eigenvectors of this linear map. Okay, so why is this true? Well, what is the matrix of a linear map with respect to some basis? So this was, I need to consider F applied to the first basis vector. So this is an element in the vector space V. And then I need to consider its coordinate vector with respect to this basis. And then the second entry is F applied to the second basis vector. And then I consider the coordinate vector with respect to the basis up to F applied to this last basis vector. And then the coordinate vector. But what is the coordinate vector F of Bi? Well, F of Bi is, by assumption, is di times Bi. So I need to ask, what is the coordinate vector of di times Bi? Oh, here's a B. So, and remember, calculating the coordinate vector with respect to some basis meant I need to ask myself, how can I write this element in the vector space as a linear combination in my basis? But here, this is just a multiple of one basis vector. So this just means this is exactly the vector which has the entry di at the ith position, and the rest is 0, because it's just di times the ith basis vector. But this already proves the lemma, because now this entry here is the vector d1, 0, 0, 0, this vector is 0, d2, and so on, and this vector is 0, 0, 0, dn. So this shows the one direction. If I have a basis like this, then the matrix with respect to this basis has this form. But also the other direction, if f is diagonalizable, this means there exists a basis such that this looks like this. But then this but then this basis is exactly given by a basis of eigenvectors. So so the statement we proved here now, and what you need to remember, is the following equivalence: diagonalizable. So f being diagonalizable is equivalent to there exists a basis of eigenvectors of f for the vector space V. So this means if I cannot find a basis of eigenvectors of a linear map f, then this linear map f will also be not diagonalizable. So in our Fibonacci example, therefore, we saw that this matrix 0, 1, 1, 1 is diagonalizable because we choose this basis B to be V1 and V2, and both of them were eigenvectors, and you can also check they are linearly independent, and therefore they are a basis, and therefore this A is diagonalizable. And now another example. This is 1, this is 2. So let's take this matrix 1, 1, 0, 2. So this has, you can check the eigenvalues. The first eigenvalue is 1, and the second eigenvalue is 2. And you can check that the eigenvector to this eigenvalue 1 is, for example, 1, 0. Because if you multiply this, if you multiply this matrix with the vector 1, 0, it's 1 times this vector. And if you take this vector here, 1, 1, if I multiply this with 1, 1, I get 2, 2. So it's 2 times this vector, and therefore this is an eigen vector to the eigenvalue 2. And also these two are linearly independent, and therefore you can choose the basis B to be B1 and B2. And then you can define your matrix S to have B1 in the first entry and B2 in the second entry. And then you can check that, what is A times S? S inverse A S. So how does this matrix look like? So if I want to get the entries of a matrix, I could also see what happens if I multiply it with the unit vectors. So if I multiply this with 1, 0, for example, so this means if I multiply the matrix S with 1, 0, I get the first basis vector. So this is B1 and here S inverse. But B1 is an eigenvector with eigenvalue 1, so A times B1 is just B1, so S inverse. And what is S inverse of B1? Well, B1 is the entry of the first column of B1, so this is just the vector 1, 0. And then what is, if I multiply this matrix with the vector 0, 1, so if I multiply this matrix S with 0, 1, so 0, 1, I get the second column, so this is B2. And B2 is an eigenvector with eigenvalue -2, so this is just 2 times B2. So I can put the 2 in front, and this is S inverse B2. And S inverse B2 just means, because B2 is the second column of S, that this is just 0, 1. So this is 0, 2. And therefore, this matrix S inverse A S, because I know the values, so I know what this matrix does on the unit vectors. So these are just the columns of this matrix here. So this is 1, 0 and 0, 2. So you see here this matrix is exactly, I have the first eigenvalue there and the second eigenvalue there. Okay. So in other words, this matrix is diagonalizable, but this we already knew at this point here because these two vectors are linearly independent and therefore they are a basis for R2. But now let's do an example of a matrix which is not diagonalizable. So if I take the matrix B, 1, 1, 0, 1, so what are the eigenvalues of this matrix? Well, so how do I calculate the eigenvalues? I consider the characteristic polynomial, which was defined by the determinant where I subtract the lambdas here on the diagonal. And you see this is 1 minus lambda squared. So there's 1, 0 of this polynomial. So I just have lambda 1, which is in this case 1. And now I need to ask myself, what are the eigenvectors for this? So I need to consider the eigenspace. In other words, I need to find all vectors such that if I subtract 1 on the diagonal, so in other words, what is the kernel of 1 minus 1, 1, 0, 1 minus 1. So this is the eigenspace of lambda 1 of this matrix B. So this is the kernel of the matrix 0, 1, 1, 0. But here we see that this is the span of the vectors 0, 1, 0. So, in other words, I cannot find two different non-zero linearly independent eigenvectors because this is just a one-dimensional space. So, in other words, there's no basis of R2 of eigenvectors of B, because this span is one-dimensional, so I cannot find two linearly independent vectors. And therefore, this B is not diagonalizable. Okay, so we see that there are some examples where this trick doesn't work, and therefore if you want to, for example, multiply the nth power of this, well, in this example it's easy, but in general, if your matrix is not diagonalizable, then maybe it's not so easy to work with these matrices. Okay, so now we want to make some statement about the linearly independence of eigenvectors which come from different eigenvectors. So, so now let's assume I have a linear map F, and now I have m eigenvectors, v1 to vm, of this linear map F, which are all eigenvectors to different eigenvalues lambda 1, lambda m. And then the statement is, if they all are eigenvectors to different eigenvalues, then these vectors are automatically linearly independent. So let's prove this. And this we want to prove by induction on m, so on the number of these vectors. So the base step would be to consider the case m equals 1. So if I have one eigenvector with eigenvalue lambda 1, then the statement is this one vector is linearly independent. And because in the definition of eigenvector we didn't allow the zero vector, so this means, so the v1 is eigenvector. This means v1 is not 0, and so the definition of linearly independent means if I have a linear combination of this vector which is 0, then the coefficient needs to be 0. But this is the case because this vector is not a 0 vector, and therefore this vector is linearly independent. Because the 0 vector is the only vector which is linearly dependent, because I can multiply it with any number and get 0. Okay, so this is the base step. So now the induction step. So we assume that the statement here holds for number of vectors which is smaller than m. So assume that I have if I have a list of vectors up to VL for some number L which is smaller than m, we assume that they are linearly independent. And now we want to check that if I take m vectors that they are linearly independent. So to check if something is linearly independent, we always start with a linear combination which is 0, and then we want to show that the coefficients of this linear combination need to be 0. So we assume that we have a linear combination of these vectors vi, and I goes from 1 to m, with some coefficients ci. So now I don't use lambdas here because lambdas are our eigenvectors, our eigenvalues, sorry. So we assume this is 0 for some ci in R. And this I want to give a name. So this equation here I call equation 1. And now we will apply our linear map f to this equation here. So f of 0 is 0, so we have 0 equals f of 0 equals f of this here, so it's f of this sum, I goes from 1 to m, ci, vi. And now f is a linear map, so here we'll use f is linear. So this means f of a sum I can apply to the summons, and here I have a scalar ci times a vector. Because f is linear, I can just apply it to this vector v. So I have the sum, I goes from 1 to m, ci times, well, we don't write this, so scalar multiplication with f of vi. But now these vi's, so we assumed are eigenvectors with eigenvalues lambda 1 to lambda m, and therefore f of vi is just lambda I times vi. So I have ci times lambda I times vi. And this I want to also give a name. So this is equation 2. So here we used that these vi's are eigenvectors with eigenvalues lambda I. Okay, so now what we want to consider is we want to subtract these two equations. So what we want to do is we multiply equation 1 with lambda m and then subtract this equation. So So consider lambda m with the first equation minus the second equation. So in both equations are 0, so this actually here is, so this is 0, but this also equals, well, if I plug in now this sum here, so I have a sum, I goes from 1 to m, ci, and here I multiply everything with lambda m, vi, so this is equation 1 multiplied with lambda m, and now I take equation 2 and I subtract it, so it's minus the sum I goes from 1 to m, ci lambda I vi. So, and this is 0. And now, so what does this mean? So in other words, I have the sum I goes from 1 to m, ci, and here I have lambda m minus lambda I, vi. So I have c1, lambda m minus lambda 1, v1, plus c2, lambda m minus lambda 2, v2, plus and the last term is I have cm and lambda m minus lambda m, vm. So this here is 0, so this term vanishes. And now, because this is 0, and here I have a linear combination of the vectors v1, v2, up to some v m minus 1, but we assume that these v1 up to vl, where l is a smaller number than m, that they are linearly independent. So therefore, so this is our induction hypothesis. We have a linear combination of these vectors which is 0. This means the coefficients here need to be 0. So the induction hypothesis implies that these coefficients, cm minus ci, they all need to be 0, where this I goes from 1 to m minus 1. Because this part here doesn't play any role. But now we see that, so another assumption in the theorem was that these eigenvalues are all different, and here therefore this thing here is not 0, because cm and is different to all ci's when I goes from 1 to m minus 1. So this part here is not 0, and therefore this coefficient here can just be 0 if this ci is actually 0. So this means ci needs to be 0 for I goes from 1 to m minus 1. But then we see if all these coefficients c1 up to cm minus 1 are 0, then in this equation here we see that everything is 0 except for the last part where we have cm times vm, and this is 0. But because vm is a non-zero vector, because it's an eigenvector, this cm also needs to be 0. And therefore we get that these ci are actually 0 for all I, and not just for the first m minus 1. And therefore these coefficients are all 0, and therefore we see that these vectors v1 up to vm are linearly independent, because we started with some arbitrary linear combination of these vectors which is 0, and then concluded that these coefficients all need to be 0. And this proves the theorem. So in other words, every time when you have a linear map and eigenvectors for different eigenvalues, then these vectors are always automatically linearly independent. And this implies several things. So we have this corollary here. So let F be a linear map, and I have m eigenvalues of this linear map. So these are the different eigenvalues of this linear map F. And I consider now the case I have an n-dimensional vector space. So if all these eigenvectors, so if I have n different eigenvalues of this linear map F, so in other words this m equals n, then this F is diagonalizable. And so this corollary will be homework, but it's a quite easy consequence of the theorem we just proved, because I mean you can check that if you have n different eigenvalues, this means there are n different eigenvectors. By the theorem, they all have different eigenvalues, and therefore they are all linearly independent, and then therefore you have n linearly independent eigenvectors in a vector space V, and then they are a basis of your space. The second statement is, if I consider these eigenspaces for the eigenvalues of F, so now this m can be smaller than n. So for example, I could be in a 10-dimensional space, and I have a linear map which just has 2 eigenvalues, and then I can consider the eigenspaces. And if I take the basis of these eigenspaces and combine all of these vectors, then the statement is that all of them are linearly independent. And then the last statement is that if the sum of the dimensions of the eigenspaces adds up to the dimension of the whole space, then this map F is diagonalizable. And this is if and only if. So here you need to show 2 directions. If it's diagonalizable, then the sum of the dimensions is n. And if the sum of this dimension is n, then F is diagonalizable. But this you can also then follow from the second statement. Okay, and the first. So this is the corollary. And now we want to introduce 2 further notations. So we see here that the dimension of these eigenspaces, they might be important, because we see if they sum up to n, then F is diagonalizable. So they will get a name. But also the eigenvalues are zeros of this polynomial given by this determinant, which we call the characteristic polynomial of this linear map F. And if I have a polynomial and a zero of this polynomial, then this zero has a multiplicity. So, and this will also get a name, but first let's recall what a multiplicity of a zero of a polynomial is. So if I have a polynomial F, and lambda is some zero of this polynomial, then we know that that this polynomial F can be written as some factor x minus lambda times another polynomial g of x. And maybe this you learned in calculus. And now this lambda could also be a zero of this polynomial g. So I could again split off this factor x minus lambda. So in general, I will be able to write F as some factor x minus lambda to the k times some polynomial gx. But now I choose somehow the maximum k, meaning that this lambda is not a zero of this polynomial g anymore, where g of lambda is not 0. And then this k, so this is then the multiplicity of this 0 lambda in this polynomial f. So for example, if I have the polynomial f of x is x minus 2 cubed or x minus 5, then 2 and 5 are the zeros, and 2 has multiplicity 3, and 5 has multiplicity 1. Okay. And with this, we now introduce the following two words. So if I have a linear map F, and lambda is an eigenvalue of this linear map F, then we know lambda is a zero of this characteristic polynomial. So recall F, the characteristic polynomial, was defined as the determinant of the linear map, the matrix of the linear map F for some basis B, and then we subtracted, or maybe here we can use, let's say it was X, and we subtracted the X on the diagonal, and then lambda was an eigenvalue. This meant exactly that lambda is a zero of this polynomial. And therefore, because this is a zero of this polynomial, I can ask for the multiplicity of this lambda. And this is called algebraic multiplicity of lambda, which we denote by alg_mu, algebraic multiplicity of this lambda for this linear map F. So this is the multiplicity of this lambda in this polynomial. And then for an eigenvalue lambda, we also defined the eigenspace, so the space of all eigenvectors for this eigenvalue lambda together with the zero vector. So this was given by the kernel of this guy here. And the dimension of this we will call the geometric multiplicity. Okay. So let's do one example for this. So last time we had one example of a linear map F, which was from R3 to R3. And this was given by multiplying with this matrix A, given by this. And we saw this matrix was given by this reflection onto a plane. And we calculated the characteristic polynomial of this linear map, which was given by -1 minus lambda squared 1 plus lambda. So therefore we saw that we have two eigenvalues, lambda 1 and lambda 2, and therefore now we can say what the algebraic multiplicity of for this linear map of lambda 1. Well, we just need to see here we have the factor 2, so the algebraic multiplicity here is 2, and the algebraic multiplicity of the second eigenvalue is 1, because here we have a 1. And then we also calculate the eigenspaces. So one eigenspace of this eigenvalue lambda 1 was given by this plane here. So we see that the geometric multiplicity of lambda 1 is 2, because this plane here is two-dimensional, and the geometric multiplicity of the second eigenvalue was 1, given by this line here. So we see in this example here that the geometric multiplicities and algebraic multiplicities are the same. They are both 2 and 1. But this is not always the case, as we will see now. So for example, if we take this matrix here, or the linear map attached to this matrix, then we can ask, well, what is the characteristic polynomial here? So it's a determinant 1 minus lambda, 1 minus lambda, 0, 1. So this is 1 minus lambda squared. So we have one eigenvalue with, so lambda 1 is 1, and the algebraic multiplicity for this lambda is 2, because of this 2 here. But what is the eigenspace of this eigenvalue for this matrix A? Well, this is the kernel of, when I subtract here 1 on the diagonal, the kernel of this thing here. But this we also saw earlier, this is a span. Oops, this is a 0. This is a span of 1, 0. And therefore the geometric multiplicity here of this eigenvalue is 1. So in this case we see that the algebraic multiplicity is 2, but the geometric multiplicity is just 1. So the geometric multiplicity is smaller than the algebraic multiplicity, but they can also be the same. And then you might ask, can also the opposite happen? And the answer is no, because we have this theorem here stating that if I have a linear map F with an eigenvalue lambda, then the geometric multiplicity of this eigenvalue is always smaller equal to the algebraic multiplicity. So the dimension of the eigenspace is always smaller equal to the multiplicity of this eigenvalue in the characteristic polynomial. Okay, so let's prove this. So let M denote the geometric multiplicity of this eigenvalue lambda. So this means the dimension of the eigenspace is M. So therefore we can choose a basis. So and let V1 up to Vm be a basis of the eigenspace. So the eigenspace of this eigenvalue lambda. And so assume we are in a n-dimensional space. So now we have m linearly independent vectors in this vector space V, which are a basis of this eigenspace of this eigenvalue lambda. And we always know that if we have a collection of linearly independent vectors, we can extend it to a basis for the whole space. So we can extend it to a basis of V. So we can take these vectors V to Vm, and then we can find more vectors which I denote W, m plus 1, up to Wn, and this is the basis of V. And now we can ask, how does the matrix of this linear map F looks with respect to this basis here? So let's call this B. And then we see that if I consider the matrix of this F with respect to the basis B, then in the first m columns, similar to what we did before when we had the basis of eigenvectors, then the matrix with respect to this basis was just given by a diagonal matrix. And this is also the case here, but it's just true for the first m columns. So here I have the eigenvalue lambda on the diagonal in this block here, in this m by m block, and here I have 0, so I have somehow, maybe I have a block here of an m by m matrix, but still here I have n minus m columns, where I have something here, and here I have an n minus m times n minus m matrix. And with this, we see that the characteristic polynomial of this linear map F, this is given by the determinant of this matrix minus x times the identity matrix. So I have lambda minus x, lambda minus x here. Here I still have 0. Here I don't care. And here I have the matrix n minus x times the identity matrix of size n minus m. So I have the determinant of this. So, but how do I calculate the determinant of this? So if I want to calculate the determinant, then here, because I just have zeros here, the only possible patterns with contribution to the determinant is when I take the product of these guys. So this is given by lambda minus x to the power of m times the determinant of this part here, times the determinant of n minus x, n minus m. And now, so m was the dimension of the eigenspace of lambda, so it was a geometric multiplicity. But now we see that the multiplicity of lambda in this characteristic polynomial is greater or equal to m, because we already factored out this lambda minus x. So so we see that the algebraic multiplicity of lambda is greater or equal to m, which was the geometric multiplicity. Okay, and this is exactly what we wanted to show. We wanted to show that the geometric multiplicity is always smaller or equal to the algebraic multiplicity. Okay, so one consequence of this theorem is that if f is diagonalizable, then we actually have that all these geometric multiplicities for all eigenvalues equal the algebraic multiplicities. Because so let lambda 1 to lambda m be the eigenvalues of f, then we have the sum of the geometric multiplicities of these eigenvalues. So this sum is smaller or equal to the sum of the algebraic multiplicities, because we proved that the algebraic multiplicities are always greater or equal to the geometric multiplicities. But also this is smaller than the dimension of the space V, because the characteristic polynomial is a polynomial of degree dimension of V, and the sum of all multiplicities of a zero of a polynomial cannot be, is always smaller or equal than the degree of the polynomial. But we also learned, or this is what you prove in the homework, in this corollary, that if f is diagonalizable, then you prove, and this is corollary 5.7. So let me go back to corollary 5.7. Here, 5.7. If f is diagonalizable, then the dimension of the eigenspaces is n, but this here is exactly what we now call geometric multiplicity of f for this eigenvalue lambda j. And this n here is the dimension of V. And therefore, if f is diagonalizable, then this sum here of the geometric multiplicities equals the dimension of V. And this can just be the case if these algebraic multiplicities are always equal to these geometric multiplicities. So, in other words, we have this sum here. So this needs to be the dimension of V, but this implies that the algebraic multiplicity for all of these lambdas needs to be the geometric multiplicities of lambda j. Okay, so we see if f is diagonalizable, then the dimension of the eigenspaces is always equal to the algebraic multiplicity of these eigenvalues in the characteristic polynomial. And the other direction is wrong if we just consider the real case, but we can show that also the other direction is true if you consider complex vector spaces, So there you can show that if the geometric multiplicities equals the algebraic multiplicities, then you can also show that this linear map F is diagonalizable. But for the real case, this is not true, because we could also have examples where we don't have any eigenvalues, and then this would be true because you don't need to check anything, but still this matrix F is not diagonalizable. Okay, so that's all for today, and next time we will talk about the spectral theorem for symmetric matrices. So we will give another condition on when a matrix is diagonalizable, and this will the statement will be, if we have a symmetric matrix, then we can always find a basis of eigenvectors, and not just a basis, but a basis which is an orthonormal basis. And yes, so this is what we will do next time. See you then.